Ladies and gentlemen, we are looking at page 8 of our notes and it's notes 2.4, which are on comparing experimental and theoretical probability. So remember that theoretical probability is just the expected probability. And it's not based on an experiment, okay? So it's the expected probability or expected likelihood. Experimental probability is the probability based on an experiment. So it's based on an experiment or based on data, okay? So it says right here that the theoretical probability of rolling a 2 with a single die is 1 out of 6. However, if you try it, you suppose you will roll exactly 1 2 in every 6 trials. So I want you to think about the answer to this question. I want you guys to answer this yourself. And then we will talk about this the next time I see you guys in class, okay? So right here, so don't forget to press pause and write an answer in, fill in an answer right here, and then press play when you've written your answer in, okay? So it says right here, suppose that you toss 10 coins at once repeatedly. How many heads should occur in each toss, okay? So right here, the probability of heads right here is always, our theoretical probability of heads is going to be 1 out of 2. So therefore, we can conclude that the number of expected heads is going to equal to the probability of the heads times the number of trials. Okay, so the probability of heads is 1 out of 2, and then you're going to multiply it by 10 trials because there are 10 coins, so you would expect 5 heads. Half of 10 is 5, okay? But then it says explain why you will not necessarily see heads every time. So you won't see heads every time because it's based on an experiment, right? So every time you flip a coin, it doesn't necessarily mean that exactly half of the time you're going to get heads or exactly half the times you're going to get tails. And that's because probabilities are like averages. Most of the time, you would expect to get heads 5 out of 10 times, but it's not necessarily going to happen, okay? But here's the thing that's really important. The higher the number of events, the closer you'll get to an even split between heads and tails. So, for example, if I flip a coin 10 times, I wouldn't necessarily expect to see heads 5 times, okay? But if I were to flip a coin 1,000 times, I might get closer to a 50% probability of heads because I've done it so many times. The individual events are going to balance each other out eventually, just like averages would balance each other out, okay? All right, so let's take a look at a couple examples. So this question right here says a modified dartboard has equally spaced sectors containing the numbers 1 through 20. So that means that each number has an equal probability. So each number has an equal probability. Okay. So what is the theoretical probability of hitting the numbers 18, 19, or 20? So this right here, the probability of getting 18, 19, or 20, remember, we're just going to do the number of successes over the number of possibilities. So we could get, if we get 18, 19, or 20, then there are 3 options for success out of 20 altogether. So the probability, the theoretical probability, is 3 out of 20. And if we were to calculate what that would be, if I take 3 and divide that by 20, I end up getting 15%. So that's important. It's important to put it as a percent so we have an easy way of comparing our theoretical probability with our actual experimental probability. Okay, so part B says in 75 of the first 80 throws, a dart player hit the numbers 18, 19, or 20. So now we're going to find the experimental probability of hitting 18, 19, or 20. So the experimental probability of 18, 19, or 20, this time the number of successful throws was 75 out of 80, okay? Both of these numbers are divisible by 5. So I end up getting 15 out of 16. So you have a probability of 15 out of 16. Now let's calculate what that is as a percent. So that's about 94%. So theoretically, we would expect that 15% of the time you're going to hit 18, 19, or 20. But experimentally, it's a totally different case. It's 94% of the time. So part C says, would you expect the experimental probability to approach the theoretical probability if the number of throws increased? And we want to explain why. So if you have control over it, you probably are not going to expect that to happen. So in a dartboard, you have control. You can aim at the 18, 19, or 20. But when you're flipping a coin, you don't really have control. Whatever you get is whatever you get. So when you flip a coin, you'll expect it to get closer to 50%. But when you're aiming at a dartboard, you don't necessarily expect it to be 15% right here because you are specifically trying to get 18 or 19 or 20. Okay, so right here, we're going to say no because each outcome's probability is now based on where the player aims. So there's a drastic difference between our theoretical probability, where each number has an equal probability, and our experimental probability, where it's based on where the player aims. Okay? All right, another example right here. How many girls? So suppose a couple would like to have 3 children. Determine the theoretical probability of having 2 girls and 1 boy. So let's go ahead and draw a tree diagram of what's happening, okay? So here we've got child 1. Okay, and we're just going to simplify it and say that we've got 2 choices, boy or girl, okay? And then after the couple has their first child, they're going to have a second child because they have 3 children. So regardless of whether it was a boy or a girl the first time, the second time, off of each one of them, we have 2 options, boy or girl, just like we had for heads or tails, okay? And then for child 3, and this is our last one, off of each one of these, we have, again, 2 options. Boy, girl, boy, girl, boy, girl, boy, girl. So, again, we end up getting 1, 2, 3, 4, 5, 6, 7, 8 options, or 8 outcomes. So let's list out what our 8 outcomes are. So our first outcome right here, boy, 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 is what we'll write down right here. Our second outcome that we have here is boy, boy, girl. Okay. Our third outcome is boy, girl, boy. And then our fourth outcome right here is boy, girl, girl. We also can get, the couple can also get girl, boy, boy. They can get girl, boy, girl. They can also get girl, girl, boy. Or they could get girl, girl, girl. So it says to determine the theoretical probability of having 2 girls and 1 boy. Probability of 2 girls followed by 1 boy is going to be as follows. First of all, it's going to have to be out of 8 because there are 8 different outcomes. And I'm going to see which outcomes here end up having 2 girls and 1 boy, and it doesn't say what the order has to be. So in this example right here, outcome number 4 has 2 girls and 1 boy. Outcome number 7 has 2 girls and 1 boy, okay? And outcome number 6 also has 2 girls and 1 boy. So the probability would end up being 3 out of 8. And if I want to calculate what this is as a probability, as a percent, excuse me, I just have to divide it all out. So the probability of 2 girls and 1 boy, like we figured out right here when I divided 3 by 8, is about 38%. Okay, so part B says explain how your answer in part A can help to determine the theoretical probability of having 2 boys and 1 girl. Okay, so if the probability right here of getting 2 girls and 1 boy was 3 out of 8, the probability of getting 2 boys and 1 girl is pretty much the same probability because it's pretty much kind of like the same event, right? So 2 boys and 1 girl is still going to be the same thing as 2 girls and 1 boy. So we can find the probability of 2 boys followed by 1 girl the same way we get the probability of 2 girls followed by 1 boy. Okay, so part C, determine the theoretical probability of having at least 1 girl. Okay, so this time I'm going to highlight all the ones that have at least 1 girl. Okay, so let's go ahead and do that. Let me just erase these really quickly. So all the ones that have at least 1 girl, this one has at least 1 girl, outcome 3 does, outcome 4 does, outcome 5, 6, 7, and 8. All of these have at least 1 girl. So the probability of having at least 1 girl is going to be 7 out of 8. And if I were to divide that out, I end up getting about 88%. Okay? Now it says to determine the theoretical probability of having 3 girls. So the probability of 3 girls is much smaller. There's only one outcome that ends up with 3 girls, so it's 1 out of 8. And if I were to divide that out, I get 12.5%, so that's about 13%. Okay? So then part E says, suppose the couple hopes to have a boy first and a girl second. What is the likelihood or probability of that? So it doesn't matter what the couple gets third, okay? So let's go ahead and highlight all the ones that have boy first, girl second. So outcome 1 doesn't, outcome 2 doesn't, outcome 3 does, has a boy first and then a girl second. Outcome 4 has a boy first and then a girl second, okay? And then all the outcomes, all the remaining outcomes have a girl first, so none of the remaining outcomes will work. So that means that the probability of having a boy followed by a girl is going to be 2 out of 8, or that simplifies to 1/4, which you guys should know is 25% because a quarter is 0.25, like a quarter is 25 cents. Okay, and that's it for this lesson. Let me know if you have any questions, and I will see you guys next class. Okay, bye.